Hey guys, so welcome to the first video in the series where we're actually going to be doing some calculus topics that you'll do in the course. So the course always starts off with the idea of limits. So limits um, is is the first starting point for introductory calculus, and lots of times when people first see that epsilon delta definition of the limit, they can get really confused. And so that's why it's important to have that intuitive understanding. And so when you see that formal definition, it's really just that same thing as your intuitive understanding. And so the whole idea of the limit is it's exactly what it sounds like. It's a limit. It's what is that function approaching as the input is approaching something specifically. And so like as an example, I find it can be really helpful to think about these things visually. So let's look at a graph for a second. Um, let's make some function with a hole in it, and we'll call this f of x. And that little place where the hole is, that's a. So we're really interested in what is the limit of x approaching a. So a specific input a of this function f of x. And the whole idea with this limit is it's what's happening around that point a. It's what's happening really close to a. So even if this function is defined, and let's say it just has like a single point, like somewhere up here, that doesn't matter. Like you don't care if the function's actually defined at this point. If the function exists at this point, if it's defined like somewhere else, it has that weird jump, like it doesn't matter. Or if it's a straight line, the whole point of the limit is it's what is happening close to that point. As that input is getting close to that specific input, what's going on in the function. And so let's say for here, this whole is at point L. Well, then this limit is L. And the whole idea is that because this function gets arbitrarily close to that point L as these x's get arbitrarily close to A. That's really what the whole idea of the limit is. And that's all that the epsilon delta definition is saying. So here, so let's break this down for a second. So for every epsilon greater than 0, so every small number, so like epsilon can be any number, you can get arbitrarily small, arbitrarily close to 0. And that goal is that we want the difference between this function f of x evaluated near that point. So there exists a delta, which means that as x is within a certain distance from a, as x is really close to a, then this can be any distance you want. You can say that the values of this function is any distance, and that's what makes it the limit, because as it gets so close, it's approaching. It has that infinitesimal distance from that thing that it's approaching, which, yeah, and that's the whole idea with what the limit is. And so uh you're only gonna have three options when evaluating limits in this courses. And so hang on, I'm just gonna say, so like this definition, this is equivalent to saying the limit of x approaching a, within that little distance between x and a of f of x is the point L. That f is getting arbitrarily close to L as x gets close to that point. But yeah, you really just have three options for limits. So either the limit is a finite point, which is like that. Like that example of that graph we just saw. Or your limit is infinity, so either positive or negative infinity. or your limit does not exist. That's usually written D and E. And so these are really like the three kind of options you're gonna have like in this class for what's going to be happening with the limit. And the main idea with how to evaluate these is you're always going to try and look to see if that limit exists and it is a finite point, because that's always like the nicest case. And so you want to really see like, well, first of all, like, is this a smooth function where it's, you know, it's defined at that point? Like if we have, so this is case number one. Let's start with one. Um, so if we have, let's say, what is the limit as x approaches a of f of x, where in this case, that f of x is just a straight diagonal line. Let's say f of x equals x. That is like the most simple, like, function, or I mean, I guess like just 0 would be simple, but still, this is like a super simple function. So right here, this is the limit of x approaching a of x. Well, it doesn't matter what a is. Like this limit is just going to equal a, because as x gets close to a, then this function is x, so it's getting close to a. That would be like the same thing if this was x squared, then this would be getting close to a squared. So that's always like the simplest case, is just if it's smoothly transitioning into it. But the main idea in this class is you're usually going to end up with cases where if you try to substitute it in directly, you end up getting 0 divided by 0. And that's really ugly. Like, this is what you need to look out for. This is like the warning. Uh-oh, something's not going on well over here. So this is your warning flag that you need to do something else. And so in this course, what you're gonna do is you're gonna somehow try and cancel like whatever is giving you this 0 over 0, because that's the thing that's making it look ugly. And so like a really common example of that would be factoring. So when you have some polynomial over some polynomial, so let's say if we have a limit of x approaching 2 of x squared minus 4 divided by x minus 2. Well, right here, like if we just tried to sub it in, we would get, okay, so we have 2 squared, that's 4, minus 4, we have 0 on the top, and then we have 2 minus 2, which is 0 on the bottom. Boom, red flags, this is not good, we need to cancel something out. And so what we do is we'll factor it. So we'll say that this is equal to the limit of x approaching 2 of, this is the difference of squares right here. So because this is x squared minus 4, and 4 is just 2 squared. So the difference of squares is just x minus 2 times x plus 2. Now, since we have an x minus 2 in the denominator and an x plus 2 in the numerator, we can, or yeah, an x minus 2 in the denominator and an x minus 2 in the numerator, we can just cancel this out. And so now all we have left is that x plus 2. And so this limit we can just sub in exactly. So that's just going to be 4, because 2 plus 2 is 4. So this limit exists and it's 4. And it's really important right here that I kept writing limit, like as you're doing the steps, because if I just factored this function, if I just said x squared minus, or let's have it factored. If I have x minus 2 plus x plus 2 divided by x minus 2, it is incorrect to say that this equals x plus 2. It's incorrect just to cancel these two things out. The only reason it's correct up here is because we're taking the limiting case. And so the reason why this is incorrect and this is correct is because these are not the same functions. So this is one function and we're saying, if we want to say it's equal to that other function, it's not, and that's because their domains are different. So even though the functions kind of look the same everywhere, this function is not defined at that point x equals 2, but this function is. This function is 4. And so we can't say that those two functions are equal, but we can say that their limits are equal because everywhere near 2, they're equal. And so that's why we're able to do this nice little trick. And that's really all you're going to be doing with limits is just these little tricks to try and cancel out the thing that's giving you 0 over 0. And yeah, and one method of doing that is just factoring and canceling. Another really common method is it's the rationalization. So whoops. If I have limit of x approaching, you have the limit of x approaching 5 of the square root of x minus 1, all that square root minus 2, and this is all divided by x minus 5. Well, again, if we just sub this in, then we'll get, 4 here, the square root of that is 2, minus 2 is 0, and then on the bottom we get 0. So we get 0 over 0, uh-oh, red flags going off, what can we do? So the way that rationalization works is you're essentially you're kind of doing the opposite of what we just did right here. Is we factored out that difference of squares. Right now we're going to create a difference of squares. So we're going to multiply the top and the bottom by its conjugate of the square root. So that's always so you're going to look at where that square root falls, and all you're doing is swapping that negative sign with a positive sign. Plus 2, and that's the conjugate. And now we're making this a difference of squares, and that's why it's called rationalizing, because we're getting rid of that square root symbol. And so root x minus 1 plus 2. And so right now we see we're making this a difference of squares, so this is going to become squared, and this is going to become squared, so that'll be that squared, which makes that 4. And so now what do we have here? We have x minus 1 minus 4. So that's just x minus 5. And then boom, x minus 5 on the top, x minus 5 on the bottom. These limits of these functions must be equal. So those cancel out. And now we can just evaluate this specifically. And we get 1 over root of 5 minus 1 is 4. 2 plus 2 is 4, so 1 over 4, that's our limit. And so it's really, again, all you're just looking to do is cancel stuff out. That's giving you that ugly 0 over 0. And if there's a square root sign somewhere in it, you're going to do this method. You're going to do, let's rationalize it. If you just have a polynomial over polynomial, try and factor it out and see what cancels. That's really all you're going to be doing when this exists. Something I really want to emphasize right now, because people get confused about this, is the problem is only when it's 0 over 0. If you reduce something and you get, you know, a constant that's not zero. So let's say like 1 over 0. This isn't a problem anymore. This means that, you know, either it's going to be an all this means is that it's not a finite point. It's either an infinite point or it's a non-existent limit. Um, and then people will also, they get kind of tripped up when they get 0 in the numerator, but then something, you know, like 4 in the denominator. That's not a problem either. That's just 0. Like when you get 0 in the numerator and non-zero in the denominator, then boom, you have your answer. It's just 0. So I really want to emphasize that because people will get really confused because they'll try and solve for a limit explicitly and then be like, oh, I'm getting 0. I need to cancel something out. No, like you only cancel things out when you get this 0 divided by 0. If it's just 0 in the numerator, then perfect, like you're already done. But when it's 0 in the denominator, then that just means you have one of those other two. You have either an infinite or a non-existent limit. And so when it's an infinite limit, actually, these are pretty much going to be the same thing. Like 2 and 3. Like you're going to tell that it's either, well, I mean, yeah. So when you're confused about whether it's an infinite limit or non-existent, you're gonna just check to see if it exists. And so the way that you do that is seeing if the right side, if the right limit, so the limit as it approaches the right is equal to that limit as it approaches the left. So let's look, for example, at the limit. Let's do an easy one of x approaching 0 of x divided by x squared. Well, if we sub this in directly, we're going to get 0 over 0. So, we can't do that. However, we can very easily cancel out one of the x's. So this is the limit of x approaching 0 of 1 over x. And now if we sub that in, we get 1 over 0. So boom, even though this isn't our answer, we know that we don't need to cancel out anything more, that this is either going to be infinite or non-existent. And now we're going to be looking at the if it's going to be like positive or negative infinity. We know that this is some type of asymptote. So the limit as x approaches 0 from the positive side, what's that going to be? Well, if x is positive, then this number right here is positive. So if we're slightly above 0, this number is positive. So that means that this is going to be positive infinity. As x approaches 0 from the negative side, so if x is very slightly below 0, well, it doesn't matter. This whole thing is negative, which means that this limit is negative 0. And so since the right limit does not equal the left limit, we would conclude the limit does not exist. But that's all you're doing anytime you have these asymptotes, is you're just seeing, okay, well, is it positive or not? Like, we know that it's blowing up. We know that it's like, if we have 1 over 0, we know that that's just an asymptote. So is it the case where it's so if this was, what's the limit of x approaching 0 of 1 over x squared? So since x is being squared here, we know that if x is slightly above 0, this whole thing is positive. If x is slightly below 0, this whole thing is positive. And we know that, you know, this is 1 over 0, so it's blowing up. But since it's positive from both sides, the limit exists, and it's just positive infinity. And so that's the main idea that you're going to be checking with that. For piecewise functions, when the limit doesn't exist, all you're doing is checking on the limit of either piece. But I'm actually going to talk about that in the video on continuity. So this is the main thing that I want to emphasize here, that I wanted to stress about limits. Like, this is all this is the essence of limits. This is all you're really going to be doing. The next video we'll talk about squeeze theorem, and we'll look at continuity too. But you know, when you're just solving for limits, these are really the main strategies. Is you're either going to get a finite point, an infinite point, or it does not exist. And if it's a finite point, all you want to do is just figure out how you're getting 0/0, cancel that out, and then get to a point where you can just sub it in by doing these like functions which have limits equal to your function. And so if there's a square root sign, you're going to rationalize. If it's just a polynomial, you'll factor. If you just have like fractions, then you know, find your common denominator, whatever. And then if you just have like something over 0, then that's an asymptote. So it's blowing up. So it's either positive or negative infinity, or it doesn't exist. And so you're just doing the test of whether it exists. You're just looking at what the sign is. So that's really just all I wanted to emphasize in this video. I find lots of people get really tripped up, especially with just getting 0 in the denominator. That's fine. Like that's fine. Like all that means is it's an asymptote. Like boom. Like you're so remember like what that looks like if we have an asymptote. So let's draw the graph of 1/x. So it looks like this, right? It's going to look something like that. So as we approach 0, it blows up. And we see that this is going to positive infinity, this is going, so this doesn't exist. In 1/x squared, it's going to look something like that. So it has that asymptote that blows up because it's 1/0, but they're both blowing up positively. So the limit exists, it's just infinity. And yeah, and just again, what is the limit? That's how I introduced the video. That's how we'll close it. Just making sure you're comfortable. All the limit is saying is, what is the function doing really close to this point, really close to this input? It might not, like in this case, it's not defined. So if we say, what is 1/0? Well, that's not defined. That's like, you can't say that. But however, you can say that the limit of this function is infinity, because really close to it, it is defined and it's just blowing up without bounds. And so that's all. It's the whole idea of limits. I hope this kind of like helped. I hope this gave like some insight as to like what you're expected in the course to do with limits. And yeah, all right.